Welcome everyone in this video lecture series of data structure. In today's lecture, we will discuss about polynomial representation and different operations that can be done on polynomial. So basically, this is one use case of array data structure. Okay, so we have already learned the concept of array and we will learn how to use that array to represent a polynomial. I think all of you familiar with the term polynomial, right? So basically, polynomial is formed with three building blocks, and these are the coefficient, exponent, and a variable. And we combine these building blocks using multiple arithmetic operations like addition, subtraction, multiplication. Okay, so a generic representation of polynomial can be written as like this: an x to the power n, an minus 1, x to the power n minus 1, and dot 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 so on up to a1 x to the power 1 and a0, which is a constant term, or we can say this as a0 x to the power 0. So basically, this an minus 1, a1, a0, these are the coefficient. Basically, we use real number to represent this coefficient of the polynomial. Here, x is a variable. So that means in each and every term of the polynomial, there exists one x, but we can provide different value for this x. And based on the value of the x, we will get different magnitude for this polynomial. Okay. And this n minus 1, these are the exponent. Okay. So basically we consider n is a non-negative integer. And this is also called the degree of the polynomial. So that means the this value n is represent the degree of the polynomial. For example, if we have expression like this, 7x cubed plus 2x squared plus 1 or plus 1 into x to the power 0. So this is one real example of the polynomial. So the degree of this polynomial is 3. So where we can use this kind of polynomial? Basically, we can use this type of polynomial to represent a cost function. For example, I want to represent how many times we have to perform iteration on a particular array to perform, let's say, bubble sort. Okay, so we know if we want to perform bubble sort, we have to perform half n square plus half n number of iteration to sort that array, either in ascending or descending order. So this cost is represented by a polynomial. Okay, so my question is that how can I store this type of polynomial in computer system? So we have to use a particular data structure for this, right? So we will learn, initially we will learn how to store a particular polynomial in a computer system. Then we will learn how we can perform different operation on that polynomial. Now you may say what kind of, why we should store a polynomial? Let's say there exists a polynomial, its equation is known, but we want to find out which is the root of that polynomial. A polynomial may have multiple number of root, but I want to find out one real root of the polynomial. So in that case, we can apply different kind of numerical methods. The crude method is the bisection method. So basically where we find out a point where polynomial is negative, another point where polynomial is positive. And basically we try to find out the mid position, and then we check in that mid position whether we have positive value or negative value for the polynomial. Okay. Basically, we apply the logic of binary search. I think all of you familiar the concept of the binary search. Okay, so where we seeing the searching domain. So same kind of logic is applied for the bisection method. So in this way, we can shrink the searching zone for that polynomial root. Okay. So if we want to apply this kind of operation, what you have to do at first, we have to store the polynomial in my computer system. So that's the primary requirement. Once it is done, we can apply different kind of operation on that polynomial later. Okay. So I think you may suggest that Let's use a one-dimensional array to store the coefficient of the polynomial. And we can reuse the index to represent the exponent. So let's say we have one polynomial like this, 7x to the power 3 plus 2x squared plus 1. Okay. So here, degree of the polynomial is 3. So basically, at max, we may have 4 terms. So we'll just create one-dimensional array. So this part is my array, and the first row represent the index. Okay. So we will store only the coefficient. So what is the coefficient of x to the power 0? This term 1 is multiplied with x to the power 0 because something to the power 0 is always 1. So that means coefficient of x to the power 0 is 1. So we will store 1 in the index 0. Next, we should have x to the power 1. So this term is not present in my polynomial, but I can say there exists x to the power 1 and it is written like this plus 0 into x to the power 1. So that's why in the first index, we can store the value 0. So that is the coefficient of x to the power 1. Next, we have 2x squared. So in the second index, what we will store? The coefficient of x squared. And we have the last term, there is a 7 into x to the power 3. So in the third index, we can store 7. So you can say this is very memory efficient representation of the polynomial in a 1D space. Is there any limitation? Yes. There is a limitation if we have any sparse polynomial. Let's say we have a polynomial like this 5 into x to the power 100 plus x plus 9. So here degree of the polynomial is 100, but most of the terms are missing in this polynomial. That means we don't have x to the power 99, x to the power 98. Basically they present, but they are multiplied with 0. If I want to store this polynomial using 1D array, then the space wastage will be very high. Why? Because we have to create one array of size 101. Clear? Because we are using the index as the exponent. Okay. So how many exponents are possible in this polynomial? From 0 to 100. So that means total 101 number of exponent is possible. So that's why we have to create one array of size 101. But this is a sparse polynomial where most of the coefficient are 0. So in such scenario, the memory wastage will be very high. To avoid this issue, what we can do, we can use one 2D array to store the polynomial. So we can take one convention that my first row will hold the coefficient and the second row will hold the exponent. Now this is also a sparse polynomial, but in this case, we have the idea how many terms are present in this polynomial. So basically we have 3 terms. That's why we will create one two-dimensional array with dimension 2 cross 3. That means we will have 2 rows and 3 columns, right? So whatever the degree of the polynomial, we always create 2 cross number of terms dimensions to the array. Now, this representation is quite memory efficient. Okay, because the number of column is not depends on the degree of the polynomial, rather it depends on number of terms present in the polynomial. Okay, so whenever we will have parts polynomial, in that case, we will go for the 2D array to store that polynomial. Fine. Now, let's say we have stored 2 polynomial in my computer system. Okay, now I want to perform addition between these 2 polynomials. So which kind of data structure I am using? Let's say I am using a 2D array to store my polynomials. So we will discuss how can we perform addition of two polynomials. So if I want to write one algorithm, what should the input for that algorithm? We have to pass two polynomials and their corresponding term count. Okay. And this algorithm will add these two polynomial and produce a resultant polynomial. So what should be the logic? Basically, uh, before describe this algorithm, at first we should learn this thing using some real world example. Then I will discuss how to write the algorithm. Okay. Let's say we have two polynomials, P1 and P2. I want to perform addition of this two polynomial to produce the resultant polynomial. So first, what you have to do? We have to store this polynomial within a 2D array. So first polynomial is minus 3. Minus 3 is the coefficient and 3 is the exponent. So in the first column, we have minus 3, 3. Then we have minus 5, 2. Then we have 7, 0. What about polynomial 2? The expression is 5x squared minus 6x to the power 1 minus 2x to the power 0. So we will store 5, 2 minus 6, 1 and 2, 0. So now try to predict what should the number of terms in the resultant polynomial. Basically, without computing the resultant polynomial, it is quite difficult to accurately predict the number of terms in the resultant polynomial. Why? Because you can see here we have one term minus 5x squared in the first polynomial, and in the second polynomial we have plus 5x squared or 5x squared. So when we will perform the addition, they will cancel each other. And we cannot say that for each and every term, addition is possible. Let's say we have minus 3x cubed, but in my P2, there is no such x cubed term, right? So that means addition is not possible. This term will directly appear in the resultant polynomial. So that's why what we should do, we should create one temporary storage with the worst case length of my resultant polynomial. Now, what is the meaning of worst case length? So that means I'm assuming that this power present in my first polynomial, there is no match in the second polynomial. So that means all the elements of the first polynomial will appear as it is in the resultant polynomial, and this will happen for the second polynomial also. So that means the worst case length of my resultant polynomial will be length of P1 plus length of P2. Okay, so we will create one temporary storage to hold the resultant polynomial. Okay, because we have to truncate the unused spaces in my resultant polynomial. That's why we will create some temporary storage and then we will copy the valid terms from that storage to the final polynomial. Okay, so what we have to do? This is my P1, this is my P2. Their length is 3 and 3. So we will create a temporary storage of length 6. So that means always there will be two rows and number of columns will be 6 for my temporary storage. Now we will take three markers. First marker will point to the first term in my polynomial 1. So that is my I marker. There is this J marker which points to the first term in P2, and K will point to the first term in my temporary storage where I will store the summation. So we will compare the exponent pointed by I and exponent pointed by J. If they are not same, that means addition is not possible. Now, what you have to do if addition is not possible, we have to copy one element in my resultant not resultant, actually in the temporary storage. Okay, so which one I should copy? So if exponent pointed by I is greater than exponent pointed by j, then I will copy the term from my P1 polynomial. Else, I will copy the term from my P2 polynomial. Okay. So in our scenario, 3 is greater than 2. So that means we will copy minus 3 and 3, this column, from my P1 polynomial in my temporary storage. As we already consider this element, so we will increment the value of I and we also increment the value of k, but j will remain in the same place. Fine. Because we haven't processed this element, first element of the P2. Okay. So next what we will do? Next, we will compare the coefficient exponent pointed by polynomial I and exponent pointed by j in polynomial 2. So now we have 2 in the exponent in both the polynomial, right? So that means now we can perform the addition. So we have to consider the coefficient. So in my P1 polynomial, coefficient is minus 5. In my P2 polynomial, coefficient is 5. So whenever we will perform the addition, we will get 0. So if we get the summation of the coefficient is 0, that means that term will not contribute in your resultant polynomial. So that's why we will not store anything in the temporary storage. So k will remain in the same place, but we will increase the value of I and j. Because we have already processed this term, but their contribution is 0. Okay. So in the next iteration, what will happen? We will consider the um, coefficient exponent 0 in first polynomial and exponent 0 in the polynomial 2 also. So now addition is possible. What are their coefficients? 7 and minus 2. Okay. 7 and minus 2, if we add them, we will get 5. So in the resultant uh, state space or in the temporary storage, what we will store? 5. Okay. And its corresponding exponent. So coefficient is 5, exponent is 0. So look carefully. We never add these exponents. Okay. Exponents addition is not required. We only add the coefficient if exponent are same. Otherwise, we will copy the highest exponent term in my temporary storage. So now, what should be the terminating condition for this operation? The terminating condition is that if there exists valid element in P1 and P2, then we will repeat this step. In our case, what happened? We already process all the elements of P1 and P2 at a time, right? In the same iteration, we have consumed all the elements of the P1 and all the elements of P2. So this will terminate the iteration, but this may be not the case for every polynomial addition. So basically, we may have some leftover elements either in P1 or in P2. So that means for those elements, no match is present in its counterpart. So basically, we should copy all those elements in the temporary storage. Once it is done, what you have to do, we have to copy the valid elements from my temporary storage to my actual polynomial storage. Okay. So how many elements present in my temporary storage? How can I say that? Basically, this is the value of k. So we start the value of k from 0. So now it reached to 3. So that means 3 number of elements are present in my temporary storage. So basically, we will create actual storage for my polynomial 3 and we will copy first 3 columns from my temporary storage to the actual polynomial. So probably you have identified the drawback of the 2D array-based representation of the polynomial. So, what is the limitation? Whenever we want to perform operations like addition, multiplication on polynomial, in such scenario, the number of terms is unknown. So basically, we need a large size of memory as an auxiliary space for to perform this operation. Okay. So how can we overcome this thing? We can, if we have any dynamic storage like linked list, so in that case, we can add this polynomial terms as per my requirement, one by one. So in that case, auxiliary storage requirement will be less. So we will learn this thing uh, when we will discuss linked list representation. Okay. For the time being, you can just assume that this 2D array-based representation is not optimized. We can optimize it using linked list. So basically, in our linked list, we should have two elements, one for the coefficient, another for the exponent. And based on the requirement, we will create such boxes and we will add them within a sequence. Fine. So this is the concept of polynomial addition. So if I want to implement such algorithm using C programming language, what do you have to do? We have to create a user-defined type. Okay. So you may think that I want to represent a polynomial, so let's create one 2D array based on the number of terms, and then we can store the data. So in my main function, I can have one int start variable which will hold my array, and there will be another variable terms that will hold number of elements present in the or number of column present in my 2D array, because row number is always true, so no need to store that thing. But what is the problem? Basically, these two elements are very closely associated. Okay, so whenever, let's say I want to perform some polynomial addition. So in such scenario, what do you have to do? We have to create our 2D array, and based on the number of terms present in the 2D array, I have to store that value within an integer variable. So why not create a user-defined type where it will club these two things together? Okay. So why I'm giving this information? Because when you implement this concept using C programming language in your lab, you should follow a proper coding structure. So basically, I just provide you the skeleton of the code. Okay. So basically, you should create one polynomial type user-defined variable or user-defined type. So we use struct to create such user-defined type, and using type def, we want to provide a single name for this entire thing. So if type def is not present, then my user-defined type will become struct polynomial. But if I want to use a single term, in that case, I should write type def struct polynomial, then its member, and before putting this semicolon, I should provide a new name. So we can reuse the same name here. Okay. So that means my new type is polynomial. So what are the content of this type? It should have one in start pointer and in terms. So this terms variable will hold how many terms present in my polynomial, and this in start pointer will hold the starting address of my 2D array where I store the coefficient and exponent. So basically, we want to perform dynamic memory allocation. Okay, if we don't want to provide any fixed size for my 2D array. So that means in my user-defined type, there is no array associated with it. So that's why we will write one function init poly where we will pass the pointer where we want to store uh, the address of the newly created element. Okay. So this init poly will allocate space for the 2D array, and also it will initialize the number of terms, this variable. So whenever I able to store the elements within my 2D array, I want to get a visual representation of that polynomial. So for that purpose, we have print poly. So this function will take address of any polynomial type variable, and it will traverse its 2D array, and it will produce a user understandable or human understandable representation of the polynomial. I also want uh, add polynomial function. This will take uh, address of two input polynomial, and it will also accept the third polynomial address where it will store the result. Instead of returning the third polynomial, I want to accept that address of the third polynomial where I want to store the result. So I want to make this function also a void function. I already explained you why we should write void function instead of returning something from the function. This is less error prone, right? And whenever you want to deal with this polynomial, many times you have to create 2D arrays. Okay. So for my temporary storage, I need 2D array. For to represent a single polynomial, I need a 2D array. So for for each 2D array creation code, I want to write them separately. So better create a separate function for that. So this function will take row number and column number as input, but I don't want to return its address. Rather, I want to pass the address of the in star star variable where I want to hold the address of my 2D array. You can do one thing, you can make it in star star as the return type. But what is the problem? If you forget to store the return value of create 2D array, it will create a problem in your program. It may create memory leakage. To avoid this thing, better to pass the address of the in star star pointer where you want to store the result. So if I want to hold address of any in star star variable, we need in triple star type variable. Fine. So this should be the structure, and you will implement this thing in your lab. And another thing, mm, what should the program flow, right? So if I want to add to polynomial, we need two polynomial type variable, and to store the resultant, we need another polynomial type variable. So basically, this is the code for your main. You have the function signature, you have the structure definition, you have to write logic for these functions. Okay, and this is the program flow. Basically, you should have three polynomial. Then what you will do, you will scan the first polynomial, then you will print the first polynomial. You will do the same thing for the polynomial 2, and finally you will invoke this add poly function to perform the addition, and the result will get stored in poly 3. So we are passing their address. So once addition is done using the print poly function, again I want to print the result. Okay. So this limitation, I have already addressed this thing, and the formal representation of this algorithm is given here. I already addressed all the complication, all the requirements of this polynomial. Just go through it. I hope you can understand this thing. Basically, it will accept two polynomial, and in output, it will produce the resultant polynomial. We will take three markers, x, I, j, and k, and we will initialize them to 0. So x is for P1, j is for P2, and k is for the resultant polynomial. Or basically, the k will point to the elements of the temporary storage. Later, we will copy that thing in my resultant polynomial. So first of all, what you have to do, we have to create one 2D array. Okay. So this is my auxiliary space. What should the size? Size should be P1 dot terms plus P2 dot terms. Now we will write one while loop. What is the terminating condition? If P1 and P2 both have valid elements, we will continue. If any of them already reached the last term, that means if there is no any valid terms, we will stop. Then what we will do? We will check the exponent. If they are same, then we will compute the sum of the coefficient. If this is 0, no need to store that thing. If it is non-zero, we will store that uh, summation in my temporary storage, the row number 1, and we will store the exponent directly in my row 2. So in that case, I will increment the value of I, j, and k, all three. But if the summation is 0, so that means this term will not contribute anything in your resultant polynomial. So basically, we will increase the value of I and j. And if the exponent are not same, we will copy the term either from P1 or P2 based on which one holds the higher value of exponent. So if I copy the elements from P1, I will increment I and k. If I get the larger exponent from my P2, in that case, I will increment j and k. So once it is done, what do you have to do? We have to check if there exists any valid element in my P1 and P2. If any valid element is present, we have to copy them. Finally, what we have to do? We have to allocate some space for the P3, and then we have to copy the k number of elements from my temporary storage to the resultant polynomial P3. And finally, we will return P3. And within your P3, there should be a terms variable. In the terms variable, you should store the value of k. So this is the algorithm for the polynomial addition. So I have already write this code in my system. So I just share the execution sequence so that you can get the programming sequence of how you should write your code. Okay, you will get some idea from this execution sequence. Basically, I provide the same input which I have shown in the example for P1 and P2, and this is the resulting polynomial. So other operation could be on this polynomial is magnitude calculation. So in case of magnitude calculation, we need a black box where we will put one polynomial and we will supply the value of its variable. Okay. So if my polynomial is x squared plus 5x plus 2, and I want to compute the value of this polynomial in x equals to 2, it's supposed to provide me 16. Why? Because 2 square means 4, 5 into 2 is 10 plus 2. So 4 plus 10 plus 2, it should be 16. The logic is very simple. You should take one result variable and you should store this to 0. Now you have to process the polynomial array one by one. You should extract coefficient and exponent from each column, and basically you should compute coefficient into x to the power exponent, and this value you should add with result. If we do this thing for each and every term, then we will get the value of this polynomial for a given value of x. You have to use this kind of calculation in case of root finding algorithm that you will learn in your numerical analysis code. Okay, so later we will learn how to implement all these logics using polynomial using linked list. Okay, so that part I will address later. So I think you know the logic. If you learn the concept of polynomial, then you can port this code from 2D array representation to linked list based representation. Okay. Any query from your side? If you have any query, you can write me an email. Thank you.